Okay, recording is in progress, and I'm going to share my slides now, and hopefully you guys are able to see the slides that I'm projecting. Okay, so in today's lecture we will be talking about vector space, null space, span, range, row space, column space. So there are a lot of topics, very interesting topics related to vector spaces, and we're talking about spaces within R to the n, an n-dimensional real vector space. We'll also take a look at some subspace examples. So this is related to sections 3.2 and 3.3 from the textbook. So what is a vector space? So the set R to the n, right? This is an n-dimensional vector, exactly like this. So let me just show you where R to the n appears here. So R to the n is something like that. So this is a vector of real numbers, and it has n rows and one column. It's a n-dimensional vector. So this is something that we have seen before. So R to the n is a set of all n-dimensional vectors with real values. So the vector space we are going to define as a set, right? So the way we read this is R to the n, it defined as a set of all x, so that the vector x is a column vector with n elements, n rows, and one column, with the condition that all these numbers x1 through xn are real numbers. So that's our vector space. Now a vector R to the n, and this n could be 2. If it is 2, then we have a vector in R squared that would look something like 3, 2, right? A vector in R to the n is an n by 1 matrix. So we can add and scale vectors exactly as we did for matrices. So if you take a look at an example here, suppose I had a vector in R to the R squared, right? So if you have a vector in R squared, let us just take an example here, 1 and 2, right? So this is a vector in R squared. So in our case here, n is 2. If we wanted to add some other vector to this in R squared, we could add, say, 3 and -1, and we would get another vector in R squared. Over here, we are going to get 4 and 1. And similarly, if you wanted to scale vectors, we could do that as well. So suppose I scaled the first vector with 3 and the second vector with 2. What am I going to get? I'm going to get a scaled version at the output, right? So I'm going to get over here 3 plus 6, right? 9. And then I'm going to get 6 minus 2, 4. So exactly as I did for matrices, I can still add, right? I can still add and scale vectors, just as I did for matrices. So this is going to be my vector space in R to the n. That is set of all vectors in n dimensions with real components. Let's take a look at some properties for such vectors. So vector space properties. We are going to take a look at these properties, and we'll use some vectors as things that you will see in those properties. I'm using v, x, and y as 3 vectors in R to the n. So these are all column vectors, n rows and 1 column, n real numbers in each of them. 3 vectors we are considering. And we're also considering small a and small b as some scalars. And if this is a vector space, then all these properties that you see on this slide are going to hold true. So let's take a look at these properties. We start with closure properties first. If you have x that belongs to R to the n, and if you have y that belongs to R to the n, if you add these two vectors, we are also going to get a vector that belongs to R to the n. And this is something that we have seen right here, right? 1, 2, 3, -1. When we added, we got another vector which was 4, 1 that belonged to R squared. So that's your closure property. Second, if you scale any vector that belongs to R to the n, for example 2x or 3x or ax, where a is a scalar, that is also going to belong to R to the n. So for example over here, if I look at just this vector, one vector here, our vector is 1 and 2, and if I scale this with 3, 4, 5, I'm going to get the result to also be in R squared because each element is getting multiplied by that scalar. So that's pretty easy to see. The closure properties are pretty easy to identify. Next, let's take a look at properties of addition over here. If you add two vectors in R to the n, the order of that addition doesn't matter. Just as order did not matter in matrix addition, even when you're doing vector space addition, the order is not going to matter. So addition is commutative over here. Addition is also associative. So if you add y and v first and then add x, it's going to be the same as adding these two vector spaces in R to the n and then adding y later on, right? So it is associative in addition. We are assuming that x, y, and v, they are all belonging to R to the n. So we have assumed that they are all in R to the n. So each of them is an n-dimensional vector. Next, if there is a vector 0, what is 0 here? Let me just point that out. 0 over here is a column vector of n zeros, right? So this is n zeros. So 0 that belongs to R to the n, so exactly like that, and the size over here is going to be n rows and one column. And if you have a vector x that belongs to R to the n, and if you add all of these n zeros to it, okay, so this is a typo here. This is going to be x. Let me write in there. And just to indicate that this is a vector, I'm putting an underscore to that. So x plus 0 will be equal to x for all x that belongs to R to the n. Very easy to see that as well, because you're adding zeros to each element in that vector. Next, for each x that belongs to R to the n, there is going to exist a negative x that belongs to R to the n, such that x plus minus x will give you a bunch of zeros. Again, this is pretty easy to see. Let us suppose our x belongs to R squared. Say you have 1 and 2 here, and this belongs to R squared. And this is going to satisfy this, right? So if you do x plus negative x, what are you going to get? Well, you're going to get 1 and 2 plus negative 1, negative 2, let me just, which equals 0, 0. This is what? This is a 0 vector that belongs to R to the squared again, R squared again, right? So all of these are properties of addition over here. Next, properties of scalar multiplication. Let me just quickly pull up the chat box because I've not been monitoring that. So let's see that. Give me 1 second. Where is my participant list? Right here. Okay, let's continue. The properties of scalar multiplication. So now you have two scalars, small a and small b, that we are using for multiplication over this x, right? So x is belonging to R to the n. It's a column vector. And if you multiply that x with a scalar b and then multiply it with another scalar a, it's going to be the same as multiplying the two scalars first and then carrying out that scalar multiplication for that vector space x that belongs to R to the n. Next, you add up the vector spaces, then scale it with a is going to be the same as ax plus ay. So over here, we are distributing each of the vector spaces over the scalar, or over here, we are distributing each of these scalars over this vector space x. Next, you have 1x. 1x is essentially what? Each element in x, each element in that vector space is being multiplied by 1, which is going to give you back the same x. You are multiplying real numbers with a 1, get back the same thing. So this is going to be true for all x that belongs to R to the n, any n-dimensional vector. So all of these are properties: closure properties, properties of addition, properties of scalar multiplication. And if there is any set that satisfies all these properties is going to be a vector space. Questions so far? So what's a vector space? N-dimensional vector, n could be 2, 3, 4, whatever. N-dimensional vector that satisfies all these properties. It has real numbers. Now, just to be a little bit clear, what I've tried over here is to use bold letters for vectors. And while I'm writing, I'm representing that same bold letters with an underline under them. And if you don't see an underline under them, so for example, for scalars, I don't bold them. Even for matrices, I don't bold them. Let's continue. Subspaces. So you have talked about vector space, the entire vector space. What is going to be a subspace? Something that is belonging to that R to the n vector space. So let's define a subspace of R to the n. Now, if there is a W is a set of one or more vectors from R to the n, so it belongs to R to the n. W is a set of one or more vectors, right? You just need one, or you can have all of the vectors in R to the n, one or more vectors from R to the n. Then W is a subspace of R to the n if and only if the following conditions are true. So if something has to be a subspace, then it has to satisfy these two criteria. And these two are closure properties, essentially. Let's take a look. U and V, if they are vectors in W, and we are talking about W being that subspace, if U and V are vectors in W, U plus V is closed in addition, right? So let me just write that. Closed with addition. So the answer should also belong to that subspace, right? W. So you see, I'm taking two vectors here in a subspace W. If I add them, I should get the result to also belong to that same subspace W. That's one condition, and we are calling that closed with addition. And the next one is with a scalar k. So if k is any scalar, U is any vector in W, then if you scale that vector, it should also belong to the same subspace. So here it is closed with scalar multiplication, right? Closed. I can just say scaling, closed with scaling. So you add two vectors, it also should belong to the same subspace. And if you multiply a scalar with a vector in that subspace, it should also belong to that subspace. If these two conditions are true, if and only if these two conditions are true, then we can call W to be our subspace. And we'll take a look at examples where we find subspaces, and we'll also take a look at some examples that are not subspaces. So that will give you a little bit more clarity about how we can work through checking for closed in with addition, closed with scaling. Now note that the zero vector, a vector which has all zeros in R to the n, in any is going to be in any subspace, right? So this 0 is going to belong to any subspace W, because if you check this second condition over here, if you take that k to be a 0, you've got 0 times U, and you see, if you take any k, right, if that is a 0 and we wanted this times U, what are you going to get? It is also going to give you a 0 vector, right? So when you scale something with k being 0, you get the result to also belong to W. So Ku will be equal to 0, which means that any subspace W is going to include this particular 0 vector. So I've scaled this vector U. I got the answer to also belong to that same subspace. So Ku equals 0 when k is 0. All right, so that's how we are defining subspaces. And we have also said that zero vector is going to belong to any subspace W. Now let's take a look at an example of a subspace. We are going to look at a plane containing the origin, and this is important. It has to contain the origin. W be a plane containing the origin, and we are looking at it in the three-dimensional space, right? W is that plane. So imagine a plane that has U and V vectors in red and blue over here. These vectors are on that plane W. If then W is going to be a subspace of R cubed. Let's try to verify that with two properties, right? Closed with addition, closed with scaling. Now you pick two vectors, U and V, on that plane, right? So on that plane, I've picked U here and V here. What is going to happen when I add them, and what is going to happen when I scale them, right? When I add them, U and V, I'm going to get another vector that is drawn in green over here that is also going to belong to that same plane, right? So that plane is going to include U plus V, because when you add U plus V, you're going to get the answer is going to be the diagonal of the parallelogram that I've sketched. And that parallelogram essentially is on that same plane that is W, which means that this proves closed with addition. Next, what about scaling U, right? If you scale U, this goes up or it can go down, or U can go up or it can go down, but no matter where it goes, as you're scaling U and V, the results are also going to be on that same plane W, right? So KU, any vector that has been scaled, it is going to also lie in W. It is going to be, so if you consider just U, it is going to be on the line through U, right? So for example, over here, let me just sketch. What is negative 2U going to look like? Let me just say negative half U, right? What is negative half U going to look like? Well, it is going to be on that same plane, but it is going to be pointing in this direction, right? Right here. Half of the length. So I can say that this is negative half U. But as you can see, negative half U is going to be on that same line as U, but it also belongs to that subspace W. So this first criteria over here proves that it is closed with addition, and this proves that it is closed with scaling. Both of these combined, we can say that the plane W is, which contains the origin, is going to be a subspace of R cubed, a three-dimensional space. Now here we have seen this geometrically. We'll also look at it in a lot more detail algebraically in section 3.3. And we'll show that that plane has to contain the origin in order for it to be a subspace. So if origin is not included, we are not going to get a subspace essentially in R cubed. Let's move on. Questions here? Okay. Now let's take another example of a subspace. And this is working through an example, so hopefully this clarifies a few more things. Let us consider a set W which has 3 points, x1, x2, x3. So this is belonging to the space R cubed. It's a three-dimensional space. x1, first component, second component, third component, x1, x2, x3. And the criteria for this particular subspace is what? X1 should be 3 times x3. So the first value should be 3 times the last value, and x2 should be 2 times the last value. So this is essentially putting a constraint on our entire vector space. So our entire vector space is R cubed, right? So that is our entire vector space. Within that vector space, I have a subspace. That subspace has a constraint. That constraint is the first component has to be 3 times the last component, second component has to be 2 times the last component. So it's going to give me a subspace within that R cubed vector space, right? Now we need to go on and check whether with this criteria, do we get a subspace in R cubed or not? How do we check it? We check it with 3 different conditions. The first one is non-empty. Let us check whether you get something does W, the subspace, have anything or not. Let's first check that. And then the other 2 important criteria is it closed with addition? Is it closed with scaling? Because that's exactly how we define the subspace condition. So if you look at any vector in that subspace, it is going to be 3t, 2t, t, right? So I'm assuming that the last value is t. That is going to, with this condition, it is going to, so here, let me just, with this condition, it is going to give me that. I'm assuming that x3 is t. Right? And then with this condition, you are going to get that. And t is an arbitrary constant, right? So if t is if I choose x3 to be t, some arbitrary value, then that subspace is going to have all these vectors of the form 3t, 2t, ut. This also belongs to the subspace W for any t, right? So if you put any t, 1, 2, 3, of course, 0 will also satisfy because, and we have already seen that the 0 vector is going to be part of any subspace. So that is true when t is 0 here. But when t is 1, 2, 3, and so on, you will always get a vector x with first element being 3 times the last one, second element being 2 times the last one is just that first t, whatever we assume, right? So this essentially proves that W is going to be non-empty. So you can just, so for any t, right? So here we can define W, our vector space, as a set where these vectors t with 3, 2, 1, these are going to be our vectors that are included in that vector space with t being real. So if you pick t to be 1, 2, 3, we will get some values here, some vectors we will get. So that's non-empty. So we have checked that. So let me just put a tick mark over there. We have checked that. Yes, it satisfies. Next condition is it closed with addition? So I'm going to assume U to be a vector in R cubed, V to be another vector in R cubed. So they belong to W. And U and V are vectors in R cubed that belong to the subspace W, which means that they satisfy this particular criteria, right? This particular criteria has to be satisfied. Now the check is, when you add them, does the answer also belong to the subspace, which means does the answer also satisfy these 2 conditions? Let's check. So by assumption, I will assume U to be U1, U2, U3. So it's belonging to R cubed, and it's a vector in that subspace W. So it is satisfying the condition. So if it has to satisfy the condition, then it has to look something like this: 3 times the last component, 2 times the last component, and U3. And also, we'll do the same thing for the vector V. Let us have V belonging to R cubed. Then you have 3 values, V1, V2, V3. And because it belongs to the subspace W, our criteria has to be met. 3 times the last one, 2 times the last one, V3. Now, when you add them, what is going to happen? When you add them, you are going to get 3 times U3 plus 3 times V3, right here. So what we are adding is for, let me take something else, say green. For U, I have all of this. And for V, I have all of this. I'm adding them up, and when I add them up, I can pull out the scalar 3 and 2 outside. So what do I get? Right? I'm adding over here 3u3 plus 3v3. I get that. Then for the second component of the result, u plus v, I get 2u3 plus 2v3. I get that. And then u3 plus v3, I get that. Now, if you take a look here, let's observe this. I've got this to be my first component, second component, and third component, right? Let me just second one and some third one, right? So these three are my three values, and you can clearly see that the first one turned out to be 3 times the last one, second one turned out to be 2 times the last one, which means that it satisfied this criteria, essentially indicating that this belongs to the subspace W. So this is also a check. So it is non-empty and it is closed with addition. Next, let's check with scaling. Is it closed in scaling? Let us assume that we have a vector u. It is going to have 3 values and it belongs to W. So it's going to satisfy that criteria. 3 times the last component, 2 times the last component, and the last component. And we are assuming that A is a scalar. The question is, if I scale u by A, am I going to get the resulting vector to be also belonging to that subspace W? So let's start with assuming that u is u1, u2, u3. These are the 3 values in u. It belongs to W, right? Because it belongs to W, you get this. It has to satisfy. So u1 should be 3 times u3. u2 should be 2 times u3. And last one is carried over. Now, if you scale that vector with A, what do you get? A times all these 3 values, which is essentially going to give you 3au3, 2au3, au3, where A is a scalar. Now, if you rewrite this, what do you have? 3 times au3. This is using the properties of scalar multiplication for subspaces. You are just reversing that order of scalars, 3 and A. You have reversed that. So you have 3 au3, 2 times au3, au3. This is also going to belong to W because the first element is 3 times the last one, second element is 2 times the last one. So it satisfies this criteria, belongs to R cubed, and it satisfies the criteria that we have laid out to qualify to be in that subspace W. So this also belongs to W. I can also say that this is also a check mark here, right? So it has satisfied all our criteria, all our 3 criteria, which essentially indicates that this is going to be a subspace. W is a subspace in R cube where x1 equals 3x3 and x2 equals 2x3. Questions about this example? You're going to see this sort of a proof a few more times where we'll say, okay, this is we'll define a subspace and we'll check whether it is a subspace or not. So here you see our answer here, is this a subspace? Should be yes. Because it has satisfied those 3 criteria. All right, let us move on. Let us take a look at the second example geometrically. So if I assume that u is this particular vector here in 3 dimensions, u belongs to W. Why is that? Because the third element, the first element is 3 times the last one, and the second element is 2 times the last one. So u belongs to W. And where is that W? That W is going to be this particular line, right? So if you take this particular vector here in 3 dimensions, and if you add any other vector to it in that same three dimensions, I'm going to keep increase. I'm going to also be in that same space W. So if I keep adding vectors, I'm also going to be in there. So if I, how about scaling? Well, I can also scale this, right? I can go up 2 times u will be over here, negative 2 times u will be over here, but no matter what, it is going to be on that line, which I'm highlighting in green as my subspace W. So the W is going to be a line through the origin in 3-dimensional space. let's move on. So let's take a look at some more examples of subspaces over here. Now, the whole R to the n is also going to meet our criteria. So this is the subspace. So a vector space, and then we are going down to a subspace. Well, the vector space is also going to be a subspace of itself. So it is going to meet our criteria. So it's also a subspace, right? The whole of R to the n. Any n-dimensional vector uh, will satisfy our three criteria. It is obviously non-empty, it will be closed with addition, and it will be closed with scalar multiplication, with scaling. How about the set consisting just of origin? Well, if you just have origin, I'll just quickly prove that it is also going to belong to a subspace. So let's take a look at that property right here. So let me check for origin over here. So I'll start off with W, and I will say this is going to be my 0 vector. I will assume two vectors U and V that belong to W. If they belong to W, that means that U is going to equal the 0 vector, and V is also going to equal the 0 vector, which implies when you add U and V, you are going to get another 0 vector. So it's closed with addition. Next, how about scalar multiplication? So let's check over here. It is obviously non-empty because it has the zero vector. Next, for scaling, I'm going to assume that U belongs to W, and there is a scalar A. So let's check. If U is 0, it has to be in that W space. So it has to be U has to be 0. So when you do A times U, you also get A times 0, which is going to be 0, which belongs to W. Right. So this says closed with addition. This says closed with scalar multiplication with scaling, and it's obviously non-empty. So using those three criteria, we can say that the set just consists of origin is going to be a subspace. We have met all those three conditions. Next, in two space, the subspaces are either going to be the origin, we have just proved that, or they are going to be R squared, everything based on this, right? So this is essentially, let's take a look. I'm able to check this off because of this, and I'm able to check this off because of this statement, and it is also going to be all the lines that are passing through the origin. So 0, R squared, or all the lines that are through the origin. So something similar we have done before for 3 space, right? So if I go back over here, we have done this for 3 space. So for 3 space, in 3-dimensional space, we said W, a subspace, is going to be in a plane containing the origin, right? So it has to contain the origin. It is the same, but for 2 space. So same for 2 space implies in 2 space is going to be lines through the origin in that case. Now, how about 3 space? Well, 3 space R cubed, the subspaces are either going to be zeros at the origin, or the entire one. Again, they are being written based on the same 2 statements that we have made earlier. Origin, all of it, the whole of R to the R cube, because we are considering n to be 3 here, or it is going to be lines or planes that go through the origin. Next, we have done this. So far we have been talking about things that are meeting our 3 criteria. Is a subspace. Let's take a look at a set that is not a subspace. So let's see how those criteria could fail. So we have a plane over here, R cubed, that it does not contain the origin, right? So we earlier said if there is a plane in R cubed that has the origin, it is going to be a subspace. So just to break that, we'll try to consider a plane in R cubed that does not contain the origin. So in particular, we will take a look at a plane defined by this: 3x1 plus 2x2 plus x3 equals 6. That's the plane that we are considering. Let me just quickly draw a quick sketch here. So I have a three-dimensional space over here, and I can consider, say, a plane right there, and clearly it is not containing the origin. I can do all the other things. For example, I can say this is x1, x2, x3, and depending on how this condition satisfies, I can find out these 3 points. I'm sure you guys know how to do all of that, right? So that's the plane that I'm talking about. It is a plane in 3D, 3 space or R cubed, that does not contain the origin. Let's try to see if that satisfies our criteria or not. Check our criteria, 3 of them. Non-empty, is it empty or non-empty? Well, if I quickly check this, x, if I put x to be 1, 1, 1, what do I have? 1 here, 1 here, 1 here. It will meet our criteria, right? So if there is a vector here, so let me just put a blue dot here somewhere. Blue big dot. So this point here I'm using as 1, 1, and 1. It is going to be on that plane, right? So that means that it is not empty because it is satisfying this. So I can say x with 1, 1, 1 belongs to W. That means that my subspace is not empty, which means I have a plane that I can sketch. So non-empty. So it satisfies this criteria. Let me quickly put a check mark over there. Good. Next. Is it closed in addition? I'm going to consider 2 vectors u and v, and I'm going to assume that they belong to the subspace W. The question is u plus v also going to belong to W or not? Let's try to do that algebraically first, and then we'll try to take a look at how it would how we can deduce that geometrically, right? So let's do the same thing. U is in R cubed, belongs to W. So if it is in R cubed, then I can write that as a vector with 3 elements, U1, U2, U3. And because it belongs to W, I can write this statement as well. It has to satisfy the criteria of being in the subspace. 3U1 plus 2U2 plus U3 should be equal to 6. That is because of it belonging to W. And similarly for V, I have it in R cubed, so V1, V2, V3, and it belongs to W, so 3V1 plus 2V2 plus V3 equals 6. Now let's check U plus V. Question is that result going to belong to W or not? So does that result satisfy this or not? Let's check. U plus V, I have got what? I need to add let's see, this guy to this guy, and similarly this guy to this guy, and so on, right? So I've got U1 plus V1, U2 plus V2, U3 plus V3. Now what are we checking? Just checking the requirement that 3 times the first element here plus 2 times the second element here and 3 times the last element here, is it equal to 6 or not, right? Is it satisfying this criteria or not? Let's try to check. It is actually going to equal 3U1 plus 2U2 plus U3, and similarly for V1, 3V1 plus 2V2 plus V3. You get 6 over here from this, and you get 6 over here from this. So this actually equals 12, which is not equal to 6, which means that U plus V did not belong to the subspace W. So it was not closed in addition. Immediately, as soon as one criteria breaks, you can say that it is not a subspace. I don't need to go through the scaling. But so this is how you would prove that algebraically, but we can also sort of look at it geometrically as well. So let's try to consider, say, 2 vectors that belong to W, right? So I'm going to assume that there is a vector here. Let me, in black I can draw. So let me assume that U is over here. Too big. Let me just draw a thin line here. U is a vector there. Oh, come on. And then I have another vector V somewhere here that is landing on that plane. Right? So what is U plus V going to look like? Well, if you add U plus V, it is going to be somewhere here. Right? And it is not going to be on that plane. It's not going to belong to that plane. Because remember, origin is not included. So you have, if you assumed that this was U, this was V, U plus V goes out of that plane. It doesn't belong to that W. Also, you can also check, say 2 times W, right? So 2 times W would pop out, right? So U is over here, 2 times W would be again out of the subspace. So I can just maybe in green I can show that this is dash, 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 dash. This is my 2 times U. Also not going to be, so doesn't belong to W here, doesn't belong to W here, right? So it fails actually both criteria, addition and scaling. And we'll take a look at how scaling fails algebraically next. So you have U belonging to the subspace W. Let A be a scalar. Question is when you scale U, is it going to belong to the same subspace or not? So by assumption, U is belonging to R cubed, so it should have 3 elements here, U1, U2, U3, and it is belonging to the subspace W, so the criteria should be met. 3U1 plus 2U2 plus U3 should be equal to 6. So when you scale it by A, what do you get? You get A times all those 3 values, A U1 plus comma A U2, and the third value will be A U3. Now we have to check whether this belongs to the subspace W or not. To check, we are going to see whether it satisfies the equation. So 3AU1 plus 2AU2 plus AU3, is it 6 or not? Well, you get the answer to be 6A, but it is not equal to 6 when A is not equal to 1. It has to satisfy for all A. So we can say that AU is not belonging to W. So we can say not closed in scaling. And we have seen this geometrically over here, and we can also say over here we didn't need to check scaling, by the way. But addition fails, it fails. Not closed in addition. Questions about this example? So this sort of goes back and validates our point that if you have a subspace in R cubed, it has to contain the origin, right? So it has to be, the plane has to go through the origin. If it doesn't, then you are going to not have a subspace. Okay. Let's move on here. Not closed in scaling. All right, more examples of sets that are not subspaces. So over here, the axes are actually not part of my subspace. So let's take a look how we are defining that. The subspace W, set of all x1 and x2, so that x1 equals 0 or x2 equals 0. So these are axes. These are not. So let me just actually let me prove that over here. If I add another page here, so and talk about axes. So how can I prove that axes are not going to be a subspace? So the values that are on the axes. So let's take a 2D sketch here, and I'll try to put some values, say U's. They have to belong to the subspace, right? So let's say that I have a U here, say at the end, oh, come on. I have a U that belongs to the subspace. I have a V that belongs to the subspace. But when I add U plus V, I'm going to get something that is not belonging to the subspace. Right? It is not belonging to the axis. It is no longer on the axis. So scaling is going to be okay, right? So scaling is going to be okay because here, if this is U, 2U will be over here. This is V, 2V will be over here, negative V will be over here. So scaling is actually okay for axes, but it is not closed in addition. How about non-empty? Well, if you look at the first criteria over here, non-empty, well, that condition is going to be okay because clearly you have all these satisfying the criteria to be in that subspace. So that's fine. It is not empty because I have a lot of points here and on the vertical axis as well. Addition is a problem, but scaling is okay. Scaling is okay, but over here addition fails. So you can see that U plus V, if this is U and this is V, U plus V is going to not belong to the axis, not on axis. Let me write that. Doesn't belong to W. Over here, U belongs to W. V belongs to W. They are on the axis, U plus V, not on the axis. So that's how we can say this property, right? So the axes, which is x equals 0 or y equals 0, x-axis or y-axis, they are not going to be a subspace, not a subspace. And for example, you can just take a look at a point and you can prove that. Something that satisfies this or this, clearly, if you take a point here, 1, 0, that satisfies x2 being 0, right? So this point satisfies this criteria. This is a or, this, right? And then I can take another point here, which is 0, 2, which satisfies this criteria. x1 is 0 there. And if you add them up, you're going to get a point 1, 2, which doesn't satisfy either of the criteria, doesn't belong to W. So we have seen something similar geometrically. Next, set of integers. So if you have integers, for example, we are considering over here x1, x2, x3 in 3D, all of them being integers. That is also not going to be a subspace. So let me also do that for over here. So let me check integers here. Integers. So I'm going to do the same thing. I'm going to draw some axes over here. And I'll just point some, just some integers. Let's say 0, 1, 2, 3 over here and here. These are all integers, right? So I've got a point there, there. I'm just highlighting all integers here. I'm only doing it in the first quadrant. You could actually do it in all quadrants. So these are all integers. So let's say you have a vector u, which is an integer, right? So let's say you have u to be this, right? So let's say you have u that belongs to the subspace. So it's an integer. So let me just draw that over here, right? U belongs to that subspace, right? So let me just draw that. U belongs to W. So what is going to happen when you do like half of U? Half of U is going to be what? Half of U is going to be here, right? So this is the scaling properties is what I'm checking here. This is half of U. Clearly, that is not going to be an integer. So that doesn't belong to W. How about addition? Addition is going to, well, it is non-empty because I have a lot of points here. I have a lot of integers. So non-empty. Non-empty is fine. Let me just write that down. Any integer will satisfy that. How about addition? Well, addition actually satisfies, right? So if I take integers and I add them to other integers, I'm going to get integers. So I'm going to get addition is going to be okay, but scaling fails here. All right, questions about this? All right, let me go back. So the way we looked at it numerically is just take three integers, scale it. So I've taken three integers, 1, 2, and 3. If I scale it, what do I get? I get a half here, a 1 here, and a 3.5 here, or 3 divided by 2 here, right? So this is not going to belong to W because the elements are not integers anymore. Very easy to sort of check that. So integers are not a subspace, axes are not a subspace, planes that do not contain the origin are not a subspace. So we had some examples that were subspaces. For example, the zero vector, the origin, all of R to the n. And we had some, all the planes that contain, all the lines that contain the origin. So there were some examples that were subspaces, some examples that are not subspaces. Okay, let's continue here. Some alternative criteria. So instead of checking for non-empty, then addition, then scaling, what you can do is you can do some alternative criteria, which is mathematically equivalent to the same 3 check, but it is slightly worded slightly differently. Let's take a look. What we required is W to be non-empty, right? Instead of that, we could just say, we could just require that the zero vector, the origin, belongs to W, since any non-empty subspace must contain the origin. So we could just check for whether zero vector, is it belonging to W or not? And if it is, then we can say that W is going to be non-empty. So instead of requiring W to be non-empty, because we know that the origin, the non-empty subset must contain origin, we looked at that, we can just check whether zero belongs to my subspace or not. And it did, right? So for example, over here, I could quickly check that. Let's see, where was that? Right here. So if I put the 0, right, x3 is 0, x2 is 0, x1 is 0, then it satisfies this criteria. So 0 belongs to W, which means that it is not empty. However, over here it fails. Let me see. This particular 0, 0, 0, well, it doesn't satisfy. So the origin is not belonging to W over here. Let's see. Next, we could replace the addition and scaling requirements by a single requirement. What is that? Let's do both of them together. Let us scale scale vector u by a, scale vector v by b, and then add them up. Let's check whether au plus bv belongs to the subspace or not. So you're trying to do both addition and scaling closure property at once together. So for all u and v belonging to W and for all scalars a and b, does this particular result, so this is a question mark, you are checking this, does that belong to W or not? So just take a quick example of our line subspace. X1 was 3x3, x2 is 2x3, right? So the first example that we looked at, let's define u to be u1, u2, u3, and it has to be belonging to W, so it has to satisfy those two criteria. 3 times the last component, 2 times the last component, and then u3. Similarly for v, v is in R cubed and it belongs to W, so I can write v as 3v3, 2v3, v3. Now if I do this check that combines both addition and scaling, sum scalar a times u plus b times v is going to be a times u plus b times v. It is going to give us, for the first component, what do I have? 3a u3 plus 3b v3. All of this can be written like that. And similarly for the second and the last component. And if I check out now, this is my last component, last value, and the first value is 3 times that last value, and the second value is 2 times that last value, which satisfies this criteria, which means that it belongs to the subspace. So I'm good. So instead of checking for non-empty additive addition, closed-in addition, and closed-in scaling, we are trying to combine addition and scaling together, and we are checking whether the zero vector belongs to the subspace or not. So this is a quicker way of checking for the subspace criteria. Okay, let's see. Let's move on to new topics now. The new topics that we are going to talk about is a span, the space spanned by a vector. We'll also talk about range of a matrix. We'll talk about column space, row space. So in order to do that, let's try to revisit the idea of linear combinations. So linear combination is what? The way we have defined this, and we have defined this many times earlier. Let's say that we have a vector W. A vector W is a linear combination of vectors. We have R vectors over here. If it is going to be a linear combination, if we can express it in this particular form. What is that? W is some scalar k1 times v1, vector v1, some scalar k2 multiplied by vector v2, and so on up to some scalar kr multiplied by some vr. So all the k's are scalars and all the v's are vectors. So if I can express W in this form as a linear combination of the vectors, W is going to, then W, we are able to express it. That's how you do it, right? Now, for example, let us try to look at how we can express W as a linear combination of these two vectors. So W is 3, 1, negative 4, 3, negative 1, and 4. These are vectors in R cubed here, right? Vectors in R cubed. And we are trying to express W as a linear combination of some V1 and some V2. Some amount of V1, some amount of V2. Let's see. It is going to be a linear combination, and the check is over here. W is essentially 2 times V1 plus negative 1 times V2. And you can put in the numbers and check for that. So all you have to do is do 2 times V1, which is 2, 3, negative 1, and negative 1 times 1, 7, negative 6, and check whether this equals W or not, right? So is this equal to W or not? And if you run through the numbers, you will see that the result exactly matches 3, negative 1, 4, which means that I'm able to express. So all of this is V1. V1, and this is my V2. And those are my scalars that made the linear combination possible. Right? Some amount of V1, some amount of V2, add them up, I was able to get to my W. So W qualifies as a vector that can be expressed as a linear combination of V1 and V2. Let's see. And in the previous lectures, we have noted how you can find out those scalars that make that possible. With the lectures on linear independence and dependence. So let's go on. Let's next, with that idea of linear combination, let's introduce the topic of span of a set of vectors. Span of a set of vectors, or the space that is spanned by a set of vectors. Let us define a set of vectors here. We have R vectors. And we can assume that each vector belongs to R to the n here. Say each vector in R to the n. So you have R of them. So this is the particular set of vectors that we are considering. The space that is spanned by this set S of a set of vectors is all the linear combinations of these vectors. All of it. So you can have so you can have something like this. What is going to be a linear combination of these vectors? It is going to be k1 v1 plus k2 v2 plus and so on up to kr vr, right? So that is going to be a linear combination of those R vectors. And for any values of k1, k2, so on up to kr, any values, rational, irrational, positive, negative, I can do any of them. I'm going to get the entire space that is being spanned by that set S, which includes those vectors. So when I think about span, I'm thinking about all the linear combinations using the vectors in the set of vectors. And so for example, what if I have, say, example, I can put k1 to be a 1, and I can put k2, k3, so on up to kr to be a 0, right? If I do that, what do I have? My vector over here is simply going to be v1, right? So v1 over the linear combination is going to be just v1. So v1 is going to be included in the span. Similarly, v2 will be included in the span if I considered k2 to be a 1 and all the other k's to be a 0, which essentially means that any vector is going to belong to the span. But also all the other combinations. So I can take 2 times v1 plus 3 times v2 and so on up to 10 times vr. That resulting vector is also going to belong to the space that is spanned by the set of vectors. So any linear combination will be in the space that is spanned by S, the set of vectors. So this is an important definition over here. Let me just highlight. The space that is spanned by a set of vectors S is the set of all linear combinations of the vectors v1 through vr. So once you know the set of vectors that you have under consideration, then you can compute the space that is spanned by those vectors. All you need to do is do a linear combination. So with any scalars, you will be able to define the span of the set of vectors. So you can say a few words. You can say this is the space that is spanned by S, or you can just call it span of S, or you can represent that as SP of S. So let's take a look example over here. We have U and V. These are vectors in R cubed. The span of two and they are not collinear, right? So they are some vectors in R cubed. U and V are going to be what? They are going to be in the plane that contains that vector. So the span of U and V are two vectors here and here in R cube. The span of U and V is going to be the entire plane that contains U and V, right? So for example, I can take 1 times U plus 1 times V. I will get another vector over here which is on that plane. I can scale them, go back over here or go back over here. U and V are also belonging to the span. So this span, I'm using this particular plane over here to indicate that that is the plane that has those two, both the vectors U and V. And U and V are non-collinear. You can see that they are not on the same line. So U and V in the span is going to be the plane. The span over here is the plane that contains the vectors. So span of U comma V is going to be the one that is highlighted over there as a parallelogram, but it's a 3D. It's a plane in 3 dimensions. All right. So that's a span, right? Span equals linear combination of vectors. As simple as that. Any linear combination. So let's see. The span is a subspace. The span is, we are going to check this, that a span, which means a linear combination of vectors, is a subspace. Let's talk about that. and we'll prove it as well. The span W, we are calling the span of W as SP of S, span of S. So W is my subspace. The subspace is being defined. W is the subspace. And I'm defining the subspace to be the span of S. S is a set of vectors. Of a non-empty set, the set of vectors that I'm considering is V1 through Vr. These are R vectors, and each vector is in R to the n. So the theorem says that if you have this S as a set of vectors in R to the n, if the span of those vectors, which means all the linear combination of those vectors, it's also going to be a subspace in R to the n. So the span of S is going to be a subspace. So let's prove this. Is it non-empty? Well, clearly it is non-empty. Why? Because any V that belongs to S is in W. So W is non-empty. And we check this, right? So for example, over here, these were my vectors, and I assume that K1, K2, so on up to Kr were my scalars that were allowing me to represent this as a linear combination. And if I assume K1 is 1, all the other Ks are 0, I have V1 that is going to belong to that subspace. So this is going to be non-empty because with Ks being 1 and followed by all zeros, I get something. It's not that it is empty. I get V1. And similarly, any V, right? You could pick V2, V3, so on up to Vr, that is going to belong to the set of vectors. So clearly, W is not empty. The subspace, which is the span of S, is non-empty. Linear combinations of those vectors are possible. Now let's check for the next one. What is that? Let U and V belong to W, right? So they have to satisfy the criteria. What is that? They have to be, we have to be able to represent them as linear combinations of the vectors, right? So U and V belong to W. So that means that we will have to be able to do the linear combination. The question is it closed in addition? So by assumption, I'm going to assume that U is belonging to W, which means that it is a span of S, which means that I can represent U as a linear combination of the vectors. The vectors are V1 through Vr, and U should satisfy this, right? Some K1 V1 plus K2 V2, so on up to Kr Vr, you should be able to do this because I said U belongs to W, and W is a span of S. Span of S means linear combinations of the vectors. So I should be able to do this. And similarly, I can assume V. But I'm not going to use the same scalars K1, K2. I'll just use some other scalars A1, A2, and so on. So I have got A1, V1 plus A2, V2, some other linear combination of the same vectors V1 through Vr is my V. So I have U belongs to W, V belongs to W. Now for some scalars Kj and Aj, where J is 1 through R, next the check is, what about the addition? So when you do U plus V, what do you have? You have K1 plus, so U plus V, right? So all of this plus all of this. When you add all of this plus all of this, you can group the scalars for each vector. K1 plus A1, V1, K2 plus A2 times V2, plus and so on up to Kr plus AR, Vr. And as you can see, if I assume that this is some other scalar, let's say this is C1, and this is some other scalar C2, and so on up to some other scalar CR, right? Some other scalars. What do I have? I have another linear combination of the vectors, which means that U plus V can be expressed as a linear combination of the vectors in the set, which means that this is going to belong to the span of S, which means that it belongs to W, right? So that's how you can check for the addition. Closed in, yes, it is closed in addition. Next, how about scaling? So over here I can put a quick check mark, yes, and we also saw that. Next, how about closed in with scaling? U belongs to W. The moment I say U belongs to W, that means that U is a vector that belongs to the space that is spanned by the set of vectors, which means that we have to be able to express U as a linear combination of the vectors in that set, V1, V2, and Vr, so on up to Vr. A is a scalar, so the question is, when you scale A by U, is that going to belong to the span of S? Is that going to belong to the subspace W or not? By assumption, what do you have? U is, yeah, we said U belongs to W, so you should be able to do this, express it as a linear combination of the vectors in the set for some scalars K1 through Kr. What about AU? Well, when you are doing AU, all you're doing is multiplying A throughout, right? So when you multiply that by that scalar throughout, what do you have? K1A, V1, K2A, V2, and so on. And now, this can be your new scalar, and you can call this maybe M1 and M2 and M3 and so on, right? So this can be your new scalar, and so on up to this can be your new scalar, some other scalar, right? So for this I can say some MR, and for this I can say some M2 and so on. So when I did A times U, some scalar multiplied by U, I got another linear combination of the same set of vectors, which means that this is also going to belong to the space that is spanned by the set of vectors. It is belonging to W, so this is also a check. So it is non-empty, it is closed in addition, it is closed in sailing, which goes on to say the span of a set of vectors is going to be a subspace. So we have added one more thing to our list of subspaces. More on the span. If you have a span, the space that is spanned by a set of vectors S, for a non-empty set S, which has all these R vectors in R to the n, so that means that each vector is going to have n elements, right? That is going to be the smallest subspace of R to the n that contains those particular vectors. Now, this is very intuitive. The way you can imagine this is, if you are given a set of vectors, because you were able to find the span of those vectors, you were able to do all those linear combinations, that is going to be the smallest subspace of R to the n. Because if you added one more vector over here, you are going to be able to span more space than what you had earlier, right? So it is going to only increase if you increase that particular set of vectors. So we can also say that this is, in other words, every other subspace of R to the n that contains these R vectors must contain that subspace W. So the span is going to be the smallest subspace R to the n, where the span is for a set of vectors. If you added one more vector over here, Vr plus 1, the space that is spanned is going to increase. Next, the null space. So the next couple of topics are very, very important, and you will see this later on as well. One is null space and the range, right? So let's take a look at the null space of a particular matrix. So let's start with a homogeneous system of equations. This particular set of homogeneous set of equations. So this is what ax equals 0, right? So that's the matrix algebra way of writing these homogeneous set of equations. So let me just write that over here. Ax equals 0, right? A is going to be my coefficient matrix, X is going to be my R to the n column vector, and 0 is going to be my just a bunch of zeros over here, 3 zeros. So this is a set of homogeneous system of equations where I can represent that as a matrix problem Ax equals 0. What is going to be the null space? Well, the null space, null of A or NA, is essentially the solutions. The solutions are the null space for that coefficient matrix A. So everything that is going to be solving this is going to be a null space for that coefficient matrix A. Set of solutions, that's it. Null space is set of solutions for a coefficient matrix A. So we can do this particular example here. So if you start off with this particular homogeneous set of system of equations and you row reduce that augmented matrix, you will be able to get these three set of solutions. The first one will be x1 equals x2, the next one will be x3 equals 0, and the last one will be x4 equals 0 as well. And we have done this exact example in the previous lectures. What this means is I can write the solution over here for x, right? Solution as this: t some arbitrary value, t some arbitrary value, because the first two has to match, and then the last two have to be 0, so 0 and 0. So over here we have infinitely many solutions, because for any t I will get a solution in x. But what I have is I can write that x as that t multiplied by this vector 1 1 0 0. So all of these solutions are going to belong to the null space for that coefficient matrix A, where the coefficient matrix A is going to be what? 0 0 negative 2 1, 3 negative 3 9 12, last row 3 negative 3 7 and 12, right? So that particular coefficient matrix has a null space. Null space can be computed by finding out the solutions. What are the solutions? Any vector that has this particular form, 1 1 0 0, scaled by some arbitrary value t. So what we can say is the null space of A is the span of, because it's a span, right? Any linear combination, well, over here there is only one vector to combine, right? But this is our scalar and this is our vector. So the span of that single vector u, which is 1 1 0 0, right? Because for every t I will be exploring the space that is spanned by that vector 1 1 0 0. So the span of that vector u is now going to be my null space for the coefficient matrix A. You can see that? So over here, we really don't have many vectors to linearly combine. We just have one vector to linearly combine. So earlier we had, say, k1 v1 plus k2 v2 and so on. Those were my linear combination of the r vectors that was defining the space spanned by all the vectors S in S. Over here I just have one vector, so I have, instead of k I have t, and instead of v1 I have 1 1 0 0. So for any t, any linear combination, that is going to define the space. So the null space is going to be the span of this single vector u, which is 1 1 0 0. Questions about this example? How do you find a null space of a particular matrix? So if you are given a set of homogeneous equations, the solutions to that are going to define my null space. Right, so I'm trying to find out what vectors over here are satisfying this equation. And it turns out that any vector of this particular form, any linear combination of this vector is going to satisfy that. So that becomes my null space. Let's see. The null space is also a subspace. So a span is a subspace. Now a null space is also a subspace. Let's try to check this. So A is an m by n matrix, and the null space of A is a subspace of R to the n, right? So let's take a look here. How can I define this? I can say A x equals 0, and if I assume that A is a matrix of size m by n, I know that x, my vector of unknowns, is going to have the size of n by 1, and on the right hand side I will end up with m zeros, right? So what is my null space? My null space is going to be all the x that satisfy this particular equation. So the null space is going to belong to r to the n, right? So the null space over here that satisfies that equation is going to be a subspace in r to the n, because this is n, right? So this is for any matrix A. So now let's try to prove whether that particular subspace, the set of all the solutions for any given coefficient matrix A, does that qualify as a subspace or not? Does that what that means is, does that solve that equation as well, right? Does that solve this as well or not? That's what we are trying to check. So let's suppose let's check for the three criteria: non-empty, addition, closed in scaling, closed in addition. First, is it non-empty or not? Well, the zero vector is going to belong to the null space. Why is that? You see, if you have ax equals 0, if you assume that the solution here is a trivial one. What is the trivial solution? Trivial solution is, let me write over here. Trivial solution is x equals zeros, right? And this is belonging to r to the n. So it has n zeros. So this is the trivial solution. This will definitely satisfy this. That means this is going to be in the subspace. So a vector of zeros is going to belong to the null space, which means that the null space is going to be non-empty because of this. Satisfies that, right? Next, let's check for addition. Let's check for scaling. For addition, again, I'm going to assume that there are two vectors u and v. They are both in r to the n, and I'm going to start off with assuming that both belong to W. That means that both belong to the subspace. What is the subspace? Null space. Null space means it is a solution. So u and v both satisfy this equation. So a times u should equal 0 and a times v should equal 0, right? With that, I'm going to check u plus v. Does that belong to W or not? Does that also solve ax equals 0 or not? So by assumption, I know that u belongs to W, so au should equal 0. It satisfies ax equals 0. Next, v also belongs to W, so av should equal 0. If au equals 0 and av equals 0, I can also say a times u plus v will equal 0. I'm just adding up these two things. So if a times u plus v equals 0, it is essentially satisfying this particular criteria, and the solution is u plus v, right? So u plus v will also belong to W. That is also a solution. So that means that this is closed in. The null space is a subspace. Well, we checked the non-empty and then closed in addition. Next, let us check for scaling. Let u belong to W, so it is a solution, which means that I can write this: au equals 0. A is some scalar, and what we are going to check is, when you scale this u with a, is that going to belong to W or not? Well, let's do it. Au equals 0. So what about a times au? Well, a times au, we want this, right? We want, what we are checking here is this. What we are checking is, check a times au, does that belong to W or not, right? So sorry, does that equal to 0 or not? If it does, then this becomes a solution. If it is the solution, then that is belonging to W, right? So let's see. because we need to check this, let's consider A times AU. I have a coefficient matrix here. I can I can bring out the scalar. So I've got the scalar out. Then I'm doing AU. I know that AU is 0 because U belongs to W. So I can substitute that, and that results in a 0, which essentially means I can remove this. It is equal to 0, which means that AU also belongs to W. All of this to prove that the null space is a subspace. So a set of solutions for any given coefficient matrix is going to be a subspace. Next, we are taking a look at another example of null space over here. We are going to try to attempt to find the set of solutions for these two equations. This is another homogeneous set of equations, and this is already in the row reduced echelon form. So if we started off with something that was not in the simplified form, then we would have had to do some row operations, row reduction, to get it into that reduced echelon form. This one already is there. So we have got the leading variables in x1 and x3 and all the other remaining variables that you could put on the right hand side, and associate some arbitrary values with those remaining variables to find what are the constrained values for x1 and x3. So the way you solve this is solve for the leading variables in terms of the remaining variables. So I've essentially rearranged this. X1 equals 3x2 minus 4x4 minus 2x. So everything, all of this are going to the right hand side here. And similarly for x3, right? So x3 is rearranged. These are my leading variables. And all of these are my remaining variables. So I'm able to express my leading variables in terms of my remaining variables. So remaining variables can be some arbitrary values, and for any choice of my arbitrary values for my remaining variables, I will get some constrained values for my leading variables. So x1, so I've done that. Next, x2, x4, x5, x6, all the remaining variables, you can assign some arbitrary values, say STUV, right? In that case, you will have infinitely many solutions. So all the solutions are going to belong to the null space for the coefficient matrix. What is the coefficient matrix? Here you have the coefficient matrix, 1, -3, 4, 2, 1. The next row is, well, I missed x3. So here the coefficient matrix here, after you reduce it, is looking like 1, -3, 0, 4, 2, and 1. Then the next one is what? X3. So I've got 0 here, 0 here, 1 here for x3. Yeah, and then 3 and -1 and 7 here, right? So the coefficient matrix, after I reduced, it is looking like this, right? So it may have some other rows here as well, but the solution to that, right? So if this is my coefficient matrix, it is going to have all the solutions are going to belong to the null space, and all the null space, I can say, what is the null space? Excuse me. The null space is going to be the set of all x that belongs to R to the 6. Why R to the 6? Because you have got 6 unknowns, right? So if that's why you have x that belongs to R to the 6, so that these criteria are met. So if you assume that all of these guys are my remaining variables for which I have assigned arbitrary constants, right? So all of these are sort of my remaining variables. I have put in the arbitrary constants. So free variables there. And then based on that choice, I've got the solution for the leading variables. So x1 has to be 3s because, it has to satisfy this and it has to satisfy this. So x1 is 3s minus 4t minus 2u minus v. So based on my choice of x2, x3, x4, x2, x4, x5, x6 in STUV, I've got constraint value for x1, and I've got constraint value for x3. So all of this is going to be my null space. So any x that satisfies this is going to belong to the null space for the coefficient matrix A. Over here, these are how many values are there in x? Well, clearly there are going to be 6 of them, right? So x1 all the way at the top, x6 all the way at the bottom. So it's a R to the 6 space. So in this case, you have got 6 variables, x1 through x6, and we have got 4 free parameters, s, t, u, and v. Earlier, we had how many variables and how many free parameters? You see, in this guy, when we did this, we had x1, x2, x3, x4, right? So we had 4 variables here. And how many free parameters did we have? Only one free parameter, right? In t. So my solution was in 4 dimensions, r to the 4. Let me go back here, right? So what we have is 6 variables, 4 free parameters. So a 4-dimensional subspace in r to the 6. So any solution is going to have 6 values for x1 through x6, but it is going to be in the 4-dimensional subspace because you have got 4 degrees of freedom in S, T, U, and V. So we'll define dimension more formally when we start talking about section 3.5. But right now, if you start off with the coefficient matrix here, you're trying to find the null space, which means that you're trying to find all the solutions for that particular coefficient matrix. And after we did the row reductions and after we looked at the solution set here, it had infinitely many solutions. And if you want to do the leading variables expressed as some combination of the remaining variables, by choosing some arbitrary values, in this case 4 of them, for the remaining variables, you will have some constraints on x1 and x3. Any 6 values that satisfy this will belong to the null space of A. Let's continue with that example here and express that null space as a span, which means that we are trying to express the null space as a linear combination of vectors, a span, right? So we have over here the same statement, null space is a set of all x in R to the 6, where these are the values of all the 6 elements in X. This is going to be a solution set for the coefficient matrix A. Now I can rewrite this as this, right? So you see, for x1, the first value in the solution is going to be all of that. So I've written there. What is the second value in my solution? X2. What is that? S. I've written it there. Third value, I've written it there. Fourth value, T. I've written it there. U and say V, right there. So I've written the solutions in a vector form. So the null space of A is a set where x belongs to R to the 6, so that x equals this column vector. For any choice of STUV, you will get a solution. You will get a vector in the null space of A. Next, what I can do is with this, because I'm trying to go for a span, which means that I'm trying to express this as a linear combination of vectors, I can start separating out the S, T, U, and V. So I can pull out an S from all the elements here. So you see, if you pull out an S from all of these guys, there is a S here, there's a S here, but there is a no S in the rest of them. So you can rewrite X as S times 3, 1, when for the rest of them, there's no S. Plus, how about T? If you look at T, for the first element, you have -4, 0, -3, 1, zeros right there, plus U and plus V. So what were we able to do over here? We were able to express the solution set as the null space as a span of these particular vectors, right? So this is a linear combination. So you can say this as This is V1, this is where V2, this is say V3, this is say V4. So you were able to express the null space as a linear combination of those vectors. So like S times V1 plus T times V2 plus U times V3 plus V times V4, with S, T, U, and V being the arbitrary scalar values, right? Free variables, free scalars. So the null space over here is being expressed as a span, as a linear combination of those four vectors. Okay, let me talk about the range of a matrix. So another important topic with what is given a matrix A, what is going to be the range of A? So if A is a matrix M by N, the range of A is going to be the set of y's that belong to R to the M, so that y equals AX for some x that belongs to R to the N. So if you are given A, right, so a coefficient matrix, you multiply that A with any x where x belongs to R to the N, you will get all the y's that belong to the range of A. So what we are talking about over here is something like this. Let us say that I express, let me do this over here on the next slide. What I'm doing over here is I'm trying to express A as A1, A2, A3, and so on up to AN. These are columns of A. And when I do AX, what is going to happen? AX, right? So AX is going to be, I have those A1, A2, AN, the columns, and I'm multiplying that with X. That's my AX. And this can be written as X1, A1 plus X2, A2 plus and so on up to Xn, AN. These are all vectors of A, A1, A2, A3, and so on. Now you can rearrange this, and you can say X1 times what plus X2 times what. Each of these vectors, they are going to be n vectors, right? So over here you have A1, A2, so on up to AN. But each vector is going to be how many? So if you start off with A as M by N, so you have got n columns, but you have got m rows, which means that each of these are going to be n, right? M rows here, and so on to m rows here. So those are going to belong to R to the N. Which is why, if I go back over here, which is why when you do the AX, you get a Y that belongs to R to the M for some X that belongs to R to the N. This is also called the column space of A, right? What is the column space of A? Any linear combination of the vectors of A, the columns of A, is going to be the column space of A. So the range of a matrix is also called the column space of A. Note that the range of A is going to be the span of its columns. Why is that? We already saw that. We took each column and we represent that as a linear combination of all those columns, which means it is going to be the span of the column space. So range of A is the span of the columns of A. So a few ways we are saying that, right? Range of A is the column space of A, is also the span of all the columns of A, linear combinations of columns of A. So range is the span of the columns, A1 through AN, where A1, A2, A3, and so on are the columns of A. Thus we obtain this corollary. What is that? A is a m by n matrix, then the range of A is a subspace of R to the m. So the subspace of R to the m, because each value over here, each vector over here are going to be in R to the m. So when you take a coefficient matrix A and you multiply with some x that belongs to R to the n, you are going to get something that belongs to R to the m. All of those are going to be in the range of A. Let's move on. Let's take a look at consistent system of equations. I have a coefficient matrix over here, A. I'm going to look at the range where the right hand side constants, I'm going to get some condition for the right hand side constants to make it a consistent system of equations. So A is this particular coefficient matrix, and I'm defining the range of A. I'm defining the range of A as B's that belongs to R to the 3, R cubed, so that this system of equations is consistent, right? So the way I'm defining my range is this system of equations has to be consistent. Find the B's that make it consistent. That is going to be my range of A. So what I can do is I can start with this particular augmented matrix. So coefficient matrix followed by all the right hand side constants here. Start with the augmented matrix, do the row reduction, you will get this. And if you look at the last row here, we have seen this before, that in order for the system of equations to be consistent, we need this particular entry to be a 0. So in order for it to be consistent, we can say that B3 minus B2 minus B1 should go to 0. So let me sort of rewrite this over here. The way I'm defining the range is range of A is a set of y's where y equals ax, right? That's how I define the range. I just need to take A and multiply by x. Over here, I'm redefining that particular range as what are the B's so that ax equals B is consistent. That's how we are defining the range of A over here. So this is the general way you would do the range. This is for this particular example. So we know that the criteria over here is that thing should go to 0, and that is going to define my range. So the range of A becomes all B's in R cubed so that B3 minus B1 minus B2 is 0. So that is going to be the range that satisfies the range of A for A being this and the system of equations to be consistent. And you can see that the null space of this range, now you're expressing the range of A as null space of a vector. So null space of -1, -1, 1 is also going to be a solution here, right? So if you consider this to be an equation, you can say -1, -1, 1, and then B1, B2, B3. That is going to evaluate to a 0, right? -1, B1, because of this. So it is in the null space of A. So the range of A, by doing this example, we have represented the range of a matrix A as a null space of a different vector, -1, -1, 1 in this case. All right, let's talk about the row space. Row space of a particular matrix. We talked about the column space, right? The column space was essentially the range of A. How about the row space? Let's take a look at some vectors A1, A2, A3, and so on up to AM. Just for the sake of discussion, I will just put A here. I'll just do an example, quick example with some values of A. What are my rows? This is my row 1, this is my row 2, right? So that's my rows. The row space of A is essentially going to be the span of my rows, first row and second row. So the row space over here is going to be the span. We can write this as span of rows. And this what is going to be a subset of R cubed. So any linear combination of these two vectors is going to be in the row space of A, right? That's how we define span. And for that, you're going to get something in R cubed. It's going to be a subset of R cubed. Similarly, how about the range? Range over here, range of A, we defined range of A as what? If I go back here, range of A was span of the columns of A, right? So let's do a span of columns of A. In this case, I have 1, 2 for the first column, and 3, -1 for the second column, 2, 0 for the third column. And any linear combination, k1 times this, plus k2 times this, plus k3 times this, any linear combination of these three vectors is going to be defining the range of A. And that you can see that it is going to be a subset of R squared. So over here we are doing span of the columns. So we are talking about the row space here. So take each row and do a span of that, you get the row space. So because we are using the capital A for columns, we are using small a to indicate each row in A. So they are going to be A1, A2, so on up to M, right? So there are M rows in the M by N matrix A, and these vectors are going to be in R to the N. The definition is the row space of a matrix is the span of each of the all the rows of A. Since the row is the span of the set of vectors, we can write this particular theorem. The row space is going to be a subspace of R to the N. So exactly the same way as we said the null space was a subspace, and the span was a subspace. We are able to also say that the row space of A is going to be the subspace of R to the N. So let's see. So the row space, we can leverage that to write our span, not requiring all of those rows. Let's take a look at that with this very important theorem, which is if you have a matrix A, which is M by N, and let us suppose that when you do all the row reductions, you get some matrix B, right? So if if A is row equivalent to another matrix B, then their row spaces will exactly be the same. Then A and B will have the same row space, which essentially means that the row operations, the row reduction, doesn't alter the row space of a matrix. Let's do an example here quickly. If you have a matrix A, consider it to be that. If you do all the row reductions, you get this, right? So this is the row equivalent matrix to A, and we are defining that to be B. So this essentially means, based on the theorem, the row space of A should equal the row space of B. What is the row space of A? Well, the row space of A is going to be span of 3 vectors. Row space of A. What is the first row? What is that? 1, 0, 2. Second row 0, 1, 2. Third row 1, 1, 4. Right? So row space of A actually had 3 of them. And based on this theorem, we can actually say that no, we don't need the third vector. Actually, we just need 2 of them. First row and second row. The third row is anyway 0. So this is going to, based on the theorem, it equals row space of B, which is the same as span of the rows in B, which is 1, 0, 2, followed by 0, 1, 2. So we are able to over here simplify and not write it as a span of 3 vectors, but just a span of 2 vectors. So row space of A equals row space of B. Why is that? Because A and B are row equivalent. The way we went from A to B is by doing row reductions. when you do row reductions, you get row equivalent matrices. We have seen those ideas before. So the row space of A equals row space of B, which simply equals the span of the rows of B, which is the same as span of A. And you can see that, right? If you take the first row here, add it to the second row here, you get the third row here, right? Which means that the third row over here is not, it's not giving me a different span. It is the same space that is spanned. Let's see. All right, so that's all I have for you guys. I will stop the recording over here. Sorry, today we went a bit longer than I anticipated.